Welcome to my presentation. It's a joint work with Katarzyna Krasnowska-Kieraś, and I'm Alina Wróblewska. I'm going to tell you about our empirical study on information, on linguistic information which are encoded in sentence embeddings. It doesn't work. The purpose of our study was to answer the research question whether linguistic information is retained in a vectoral representation of sentences. And in order to answer this question, we used two methods. The first one was based on universal probing tasks, and the other one on downstream tasks. We conducted a lot of experiments with different types of sentence embeddings in two language scenarios, English and Polish. I start with a short explanation of the idea of probing task. A probing task is a classification problem that focuses on simple linguistic properties of sentences. The probing data set for training probing classifier consists of a set of sentences with probing labels. For example, it could be the tense of the sentence predicate, for example. So we just select all sentences with past predicate and all sentences, for example, with present tense predicate, and it's our probing data set for training a classifier. The sentences are represented as embeddings, as vectors, and the classifier is trained on those vectors as input, and the probing labels as targets. Finally, the performance of this classifier as a kind of proxy for the quality of retention of linguistic information in sentence embeddings. Now I present our probing tests. The first two are general tests used previously by different researchers, and they are based on surface properties, sentence length and word content. The first test consists in classifying sentences by their length, measured in tokens. And the second test consists in classifying sentences according to in this case, 750 classes corresponding to target words, pre-selected target words. We also have a set of, we've called them compositional probing tests. The first one, it is dependency tree depth test, and it's a classification of sentences according to the depth of a dependency tree. In the example tree, the example tree has the depth of 3. It's because the longest path consists of three arcs. The second test, it's top dependency schema. We just selected 20 multi-sets of dependence of the sentence predicate. And in the example tree, this example tree or sentence should be classified with the multi-set shown here. It's an auxiliary, nominal subject, auxiliary, and oblique. The next test is a binary classification of sentences according to the grammatical voice. We have two classes in this case. Either the sentence predicate or the sentence is passive or non-passive, and the example sentence is not passive. Then we also have a test which is a binary classification of sentences according to the grammatical tense of sentence predicate. We have two classes in this case, present and past. The example sentence should be classified as past because his start is just a past tense. Then we also have two tests on grammatical number of subjects and objects. So it's also a binary classification, and sentences are classified according to the grammatical number of subject or grammatical number of object. And the last test, we've called it sent type, and it's a classification of sentences according to their types. We have three classes: inter for interrogative sentences, imper for imperative sentences, and other for declarative and exclamatory sentences. And the example sentence should be classified as other because it's a standard declarative sentence. Okay. We wanted to extract probing data sets which are comparable for those both languages. That's why we extract them from a parallel Polish-English corpus. Then all parallel sentences are preprocessed to get universal dependency trees. They are just tokenized, tagged, and dependency parsed. And from those universal dependency trees, we've just selected or extracted our probing data sets. We designed a set of rules which are universal in terms of the schema or just the universal dependencies annotation schema, because we extracted from dependency UD trees, and the rules are compatible with this universal dependency schema. For each probing task, we selected or extracted a data set consisting of 75,000 examples for training, and then 7,500 for validation examples and testing examples. Okay. Apart from those probing tests, we also have two downstream tasks: semantic relatedness and textual entailment. Semantic relatedness is just measuring the degree of any kind of association between two sentences in this case. The predicted score, relatedness score, is evaluated against manually assigned scores, and they are evaluated with Pearson's or Spearman's coefficients. Textual entailment assess whether the meaning of one sentence is entailed in the meaning of another sentence. We have three classes here: entailment, contradiction, and neutral. And the predicted labels are evaluated with accuracy. In our experiments, we used the SentEval toolkit for testing sentence embeddings in those probing and downstream tasks. As data, we have those 9 probing data sets for English and for Polish. And we use 2 external downstream data sets. For English, SIG corpus, and for Polish, CDS corpus. We evaluate various sentence embeddings, actually 3 types of sentence embeddings. The first, they are just max pooled sentence embeddings. They are obtained by just pooling, max or min pooling over word embeddings, and we used fast text embeddings, paired and combo embeddings. We also test sentence embeddings estimated on small corpora. In this case, 3 million sentences with sent to VEC library. And finally, we also test large pre-trained sentence embeddings, sent to VEC, original sent to VEC for English, use for English, and multilingual laser embeddings for both languages. And the results. Polish results, or English accuracies are in gray cells. Polish are in pink cells. And the highest scores for each probing task are in yellow cells. And here are all models, or all sentence embeddings we've tested. Here are the results for those two simple tests. Maybe they are not very interesting, but I think that those results are maybe more interesting. Generally, the dependency parser-based embeddings are the best for encoding linguistic information, and actually it's not. It wasn't a surprise for us because we used UD trees for extracting data sets, so there is a kind of bias maybe. We also noticed that generally mean pooled sentence embeddings are better than max pooled embeddings. The second best embeddings are laser embeddings, and it was actually a surprise because they are laser embeddings are trained on large multilingual data sets. So, yeah, we don't know why they are the best, but they are. The laser embeddings are also the best in the relatedness and entailment tasks. In relatedness in Polish and entailment in both languages. Use embeddings outperform the laser embeddings, but use embeddings are also estimated on interference corpora, so there is also a kind of bias in these results. Okay, we also test, these two figures show the results for three models: BERT, sent to VEC, trained on those small sentence embeddings trained on small corpora and laser embeddings. The left plot is for English and right for Polish, and generally they are quite similar in shape, except for word content. For English, sent to VEC and laser embeddings are, they perform similarly well, and they outperform the BERT embeddings. And in case of Polish, there is a difference because sent to VEC embeddings are much better than laser and sent to VEC. We also measure correlation between results for Polish and English. Here are results per model, and here are per task. Generally, correlations per model are high, so there is nothing special. And in case of correlations per task, there are differences in three tasks. The two downstream tasks. So we suppose it could be because of the differences in data, because two corpora, two data sets for relatedness and entailment, they are similar in size, but they are created independently, so it could be the reason. And in case of sent type, actually the accuracies are very high, and they, okay, so maybe it's because of this. So I have to conclude now. Okay, so we proposed a set of probing tests which are universal because they are based on universal dependency tree banks or schema. We extracted datasets for Polish and English, and generally dependency parser-based embeddings encode linguistic information in the most accurate way, and linguistic information is well retained in the recently proposed laser sentence embeddings. Okay, and thank you for your attention.